Assalamu alaikum everyone. So we will resume our last topic, that is antennas and propagation, and we will be having lecture number 16, and these are the topics which we will be going through one by one. Dipole antenna, then we will be talking about antenna gain, and there is a strong correlation between the wavelength and the antenna size. So we will be talking about the antenna size and wavelength. Then different antennas, they provide different radiation patterns, and we have to understand the radiation mechanism in order to understand those different radiation patterns. Then we will be discussing about antenna efficiency, beam width, and we have different types of antennas, and those different type of antennas, they actually support different propagation modes. So we will be talking in details those different propagation modes. And then finally we will talk about the DIPOLE, that is the noise that is omnipresent everywhere, and we also will establish some of the techniques in order to overcome that noise. So let's talk about dipole antenna. So this is one of the most widely used antenna, and it is a half wave dipole. The half wave, it's also called doublet, and is actually invented by HERTZ, so that's why it is known as HERTZ antenna. So we have two pieces of wires, as we mentioned in the last lecture, that we can convert a transmission line into an antenna. So if we have a transmission line and we, or maybe wire, so we cut the wire in such a way that it has a length of 1/4 of the wavelength. So and then we can bend the two ends in such a way that it will be actually creating a dipole antenna. So here is the way that we can convert or we can have a transmission line that is actually converted into an antenna. So you can see that the length of each end is lambda by 4. So in total we have the lambda by 2, right? So you can see the coupling of electric and magnetic field over here, and here we have the radiation pattern. So it's not a two-dimensional radiation pattern, it's a three-dimensional radiation pattern for a dipole antenna. So you can see we have vertical mounts, and we also have horizontal mounts there. The pattern is a donut shape, so it looks like a donut with antenna passing through the center. So here we have the antenna, and the radiation pattern is actually all around the antenna. There is no radiation from the end of the antenna. So then we have to define the antenna gain. So in case of a dipole antenna, the gain is 1.64. So we actually mention gain in dBs. 10 log base 10 into 1.64 is equal to 2.15 dB. Then half wave dipole antenna has a power gain of 1.64 or 2.15 dB over an isotropic source. So this is the real ideal source, not the real one. Antenna gain reflective to a dipole antenna can be expressed in decibels. So what should be the actual length of the antenna? So as we know that antenna has to radiate energy into the atmosphere, and it has to receive energy from the atmosphere. So in both cases resonance is very important. So dipole resonates best when it is approximately 95% of the actual half wavelength. So there is a relationship between the resonance and the wavelength, right? So then we have the formula, that is the length in feet is equal to 468 divided by frequency in megahertz. And so there are some conditions that dipole should be hung vertically as closest as possible to an isotropic radiator. So bottom of the dipole antenna should be at least half a wavelength of the ground. So here we will be talking about the radiation mechanism. So ideally all the incident energy must be reflected back, but this is not the case, right? So when we talk about the open circuit, so as we have mentioned, then when we have a transmission line, so we cut the transmission line and bend the end wires to make it as an antenna. So we have a source over here, and this source is generating current and voltages, and those currents and voltages, they are oscillating to and fro. So as a result, the incident energy should be reflected back, but this is not the case. The small portion of the energy escapes from the system, and it is actually radiated into the free space in case of the transmission. So the reason for this escape is that the line of force don't have to undergo complete phase reversal, so and some of the energy, as a result, some of the energy escapes from the system. So you can see that we have the energy or radiation patterns that are being escaping from the system as a result of to and fro motion of this source. And the amount of escape energy is very small due to mismatch, because one side we have copper or metallic or conductor, and on the other side we have the free space, so there is a mismatch, right? So we can also have the concept of mismatching over here. So due to this mismatch between transmission line and the surrounding space, the amount of energy is very small that is escaped. So another reason is that the two wires are too close to each other, so radiation from one tip will cancel the radiation from the other tip. So that's why we need to keep the two ends at a certain distance in order to have maximum energy that is escaped, so that the energy from one tip cannot be cancelled by the other tip of the wire. So as they are opposite polarities and distance between them is too small as compared to the wavelength, so that is that can be one of the reason that why the small portion of the energy is radiated. So we have to take the corrective actions in order to increase the amount of radiated power. So you can see that over here, instead of the wires here, they are not bent, so we have give them more bend in order to have more space between the two tips or two ends. So the two wires, they are separated by a large distance. So as a result of this arrangement, the coupling between the transmission line, that is a metallic or conductor wire, and the free space is increased, and as a result we have the more energy that is escaped from the system, or we don't have we have very little cancellation. So also the cancellation is reduced, right, and the radiation efficiency will increase further if two conductors of transmission line are bent so as to bring them in small line. So here we have different type of antennas. So we apply those antennas according to the requirement, according to the application and technology that is the communication system is having. So mainly we have two different categories of antenna. One is the omnidirectional or only weakly directional antennas, which receive a radiator more or less in all directions. So those type of antennas, they actually are deployed when the relative position of the other station is unknown or arbitrary. So in case of the mobility, if we want a communication system with the mobility support, then we normally use the omnidirectional antenna. They can also be used at low frequencies where directional antenna would be too large, or simply to cut the price, right? So this is very important that we don't want to have large antennas, and those antennas, they are difficult to move around. So, and then we have the directional or beam antennas, which are intended to preferentially radiate or receive in a particular direction. So if we talk about the cellular communication, so we have towers, and over those towers we have two types of antennas, right? One are the directional antennas that are there, and the other one, they are the omnidirectional antennas, in order to provide communication facilities for the cellular phone. So when the different sites or different base stations, they have to communicate with each other, so for that purpose they normally install the directional antennas. So we discussed antenna types according to their applications. So now we will be having different antenna types according to the length of the transmission lines, right? So we have resonant antennas, where those antennas actually represent exactly equal to multiples of half wave lengths, and it is open at both ends. So you can take this example as a resonant antenna. Then we have non-resonant antenna. The length of these antennas are not equal to exact multiples of half wavelength, and in these antennas standing waves are not present. Standing waves are not present, as antennas are terminated in correct impedance, which avoid reflections. So reflections are minimized, so the wave travel only in forward direction. Non-resonant antenna is a unidirectional antenna, so we have one-way communication in case of a non-resonant antenna. So here we will be talking about the radiation pattern. So the radiation pattern of antenna is a plot of the relative field strength of the radio waves emitted by the antenna at different angles. Because as we mentioned that in case of the transmission antenna, for example, it radiates energy, and that energy is actually the EM wave or electromagnetic form of energy, so is radiated from the antenna at different angles. So if we plot the radiation at different angles, so we would get a radiation pattern. So in order to represent this radiation pattern, we have a three-dimensional graph, or maybe a polar plot of the horizontal and the vertical cross sections. So it is a plot of the strength versus the angle in degrees. So the pattern of an ideal isotropic antenna which radiates equally in our direction, that is not the real case, would look like a sphere. So if we take a reference, if we want to take a look at the reference, so we have the isotropic antenna that radiates equally in all directions, and of course at all angles it is radiating equally, you can say. So many non-directional antennas such as dipoles emit equal power in all horizontal directions, with the power dropping off at higher and lower angles. So this is normally an omnidirectional pattern, and we plot, we have seen that plot that is looks like a donut. So we have different loops. One of the pattern is for maxima. In order to represent the maxima, the angles at which the maximum radiation takes place, so that as loops for maxima at various angles, and they are separated by nulls. The angles where we have zero radiation. So the reason for this maxima loops and the nulls or zero radiation is that the radio waves emitted by different parts of the antenna typically interfere, causing maximum at angles, at certain angles where the radio waves arrive at distant points in phase, and zero because there they are out of phase, so they cancel each other. So that's why we have zero radiation at some of the angles, right? In a directional antenna designed to project radio waves in a particular direction, the loop in that direction is designed larger than the others and is called the main loop. So we have a main loop, maximum loop, or maybe we will be having some other loops, side loops, and we will be looking them graphically. So gain is a parameter which measures the degree of directivity of the antenna radiation pattern. A high gain antenna will preferentially radiate in particular direction. Specifically, the antenna gain or the power gain of an antenna is defined as the ratio of intensity power per unit surface radiated by the antenna in the direction of its maximum output at an arbitrary distance, and this has to be divided by the intensity radiated at the same distance by our reference antenna, that is the isotropic antenna. So the antenna gain is a passive phenomena, that is the power, input power, right? It's more, and we have the lesser output power, so that's why it's not an active phenomena, it's a passive phenomena. High gain antennas have the advantage of longer range. Of course, if we have a high gain, so it means we have the higher input power, and the ratio is also higher. And better signal quality is the case when we talk about the high gain antenna, but must be aimed carefully in a particular direction. So the efficiency of a transmitting antenna is defined as the ratio of the power actually radiated in all directions to the power absorbed by the antenna terminals. The power supplied to the antenna terminal which is not radiated is converted into heat. So this is the reason. This is usually through loss resistance in the antenna's conductor, because we have resistance, but can also be due to the dielectric or magnetic core losses in antenna. So there can be some other reasons, for example dielectric and magnetic core losses. So we have talked about the polarization, so now we will be talking polarization again, because we have to establish the radiation patterns. So the polarization is closely related to the radiation pattern, because in that case the orientation of the electric and magnetic field is associated, and we define polarization as the orientation of the electric and magnetic field. So you can say that due to the rotation of those different fields, the polarization is different. We can have vertical, horizontal and circular polarization. So as a result, we can have different waveguides, right? So that's why we can say that there can be a relationship between the polarization and the radiation patterns, because at different angles we have different radiations. So a simple straight wire antenna will have one polarization when mounted vertically and a different polarization when mounted horizontally, right? So you can see the configuration of the antenna is important. So if we mount the antenna straight wire as a simple straight wire, one polarization, and if we mount differently, then we have another polarization. So reflections generally affect the polarization. For radio waves, the most important reflector is the ionosphere. So as we know that we have reflection signals which reflect from it will have their polarization changed. So low frequency, very large frequency and medium frequency antennas are vertically polarized. Then beam width, it's actually defined as angular separation between two half power points on power density radiation pattern, or angular separation between two 3 dB down points on the field strength of the radiation pattern. So we mention beam width in degrees. So here we have shown the beam width graphically. So you can see that we have the main loop. So then we have the half power point right, and half power beam width, and then beam width between first nulls, right? So here we have half power point left, and you can see minor loops. So these are the minor loops, and here we have the main loop. So beam width between first nulls. So here we have shown the isotropic antenna. So it's a hypothetical antenna, and we normally take this as a reference, and we say that it radiates energy in all directions equally, right? So its radiation pattern is represented by a sphere as shown here, whose center coincides with the location of the isotropic radiator. So we have a radiator over here, right? And it's considered to be the point in space with no dimensions and no mass. The antenna cannot physically exist because this is not possible. Useful as a theoretical model for comparison with all other antennas. So half-wave dipole antenna, and here we have the radiation pattern of the dipole. You can see that we have symmetrical circles about the axis of the dipole, is maximum at right angles to the dipole, dropping off to 0 on the antenna's axis, right? So then we can have a folded dipole. Here you can see that the dipole is folded, single antenna, but it consists of two elements. First element is fed directly, while the second one is coupled inductively at its ends. Radiation pattern of the folded dipole is same as that of the dipole antenna, right? So here in this figure. So there are certain advantages. Input impedance of the folded dipole is 4 times higher than the straight dipole. Typically the input impedance of half wavelength folded dipole antenna is 288 ohm. Bandwidth of the folded dipole is higher than that of the straight dipole. So it supports more bandwidth. So here we have the HERTZ antenna. Short dipole, smaller than the wavelength, with a uniform current along its length. A true HERTZ dipole cannot physically exist since the assumed current distribution implies an infinite charge density at its end. That is not possible, and significant radiation requires a very high current over it for a very short length, right? So then we have the loop antenna. Is a radio antenna consisting of a loop of wire with its ends connected to a balanced transmission line. Single turn of coil carrying RF current through it. The dimension of the coil are smaller than the wavelength, hence current flowing through the coil has same phase. Loop antenna, right? So here we have the loop antenna. Radiation pattern of the loop antenna is a different pattern, can be circular or square loop. So we can have a square loop also. Here circular loop is shown. It is received normal to the plane of loop, and null is obtained in other directions. So turnstile antenna, so again, is a set of two dipole antennas aligned at right angles to each other. So two dipole antennas, they are aligned at right angles to each other and fed 90 degree out of phase. The name reflects that the antenna looks like a turnstile when mounted horizontally. Okay, then rhombic antenna. Structure and construction of this antenna is actually composed of 4 wires in rhombic shape and terminated by a resistor mounted horizontally and placed at a distance lambda by 2 from the ground. Highest development of long wire antenna is rhombic antenna. So here we have the configuration of the rhombic antennas. 4 wires, they are connected in rhombic shape, you can see, and terminated by the resistor. So at the end we have the mounted horizontally placed at a distance lambda by 2 from the ground. Okay, so there are certain advantages and disadvantages that this rhombic antenna is carrying with. Easier to construct. Its input is impedance and radiation pattern are relatively constant over a range of frequencies, maximum efficiency, so high gain can be obtained, large site area and large side loops. So we need, you can see that we need a large area. So here are the applications: long distance communication, high frequency transmission, point-to-point communication, and radio communication. So here we have the disc-cone antenna. The disc-cone antenna is characterized by very wide bandwidth covering 10⁻⁴ frequency range. It also has an omnidirectional pattern in the horizontal plane and again comparable to that of the dipole. So here we have the helical antenna. Are classified as helical. The antenna in the sketch has its maximum radiation along its long axis. So it has maximum radiation along its long axis. Quarter wave monopole can be shortened and wound into a helix. So here we can feed this is a feed point, right? So we can also have the antenna arrays is a group of antennas or antennas element arranged to provide desired directional characteristics, right? So we can also take the example that our ears, they actually are antenna arrays, one antenna and two antenna, and our brain is a processor. So actually we want to magnify the sound signal, so we are using those two different antennas. They are aligned and we hear receive signals from those different ears, and then the objective is that we want to magnify the sound in order to have a better understanding what has been communicated to us, right? So here we have the Yagi antenna, directional antenna consisting of a driven element, a dipole or folded dipole, and additional parasitic elements arranged linearly, collinearly, and close together. The refractive element is slightly longer, right? The design achieves a very substantial increase in the antenna's directionality and gain compared. So here we have the Yagi antenna. So you can see that we have a dipole. So this is a closed dipole, and these are the directors, right? And this is the reflector, right? So you can see that configuration of the Yagi antenna. So here we have mentioned the radiation pattern of the Yagi antenna. So this is the main loop, and these are the side loops, and here we have the back loop, right? So we can have a lot of different applications of antennas. We can use antennas for radio broadcasting. We can also use antennas for TV broadcasting. We can also have simplex and duplex communication when we talk about the antennas. So in case of radio broadcast, so it's a one-way communication. In case of a television broadcast, again it's a one-way communication. But when we talk about the cellular communication, so the antennas, they actually are two-way radios, right? So it's a full duplex communication. And we can also use antennas for radar, cell phones, and satellite communication. So there are some of the considerations when we talk about the antenna: the space available for an antenna, the proximity of neighbors, the frequencies which will be the operating frequencies for the underlying or ongoing communication, the power, output power the antennas are producing, and of course the last but not least, the cost, which is also very, very important. And then we have the matching, right? So when we talk about the radiating electromagnetic energy into the outer space, so there should be a matching between the between different media. So in order to have the maximum coupling, we have different configurations, different type of antennas. So the antenna matching is very important. Resonant antenna is too large to be convenient. So other times an antenna may be required to operate at several. So we can also have a wideband antenna, right? Problem of mismatch can be rectified by matching the antenna to the feed line using an LC matching network. So there are certain solutions. Reflectors. So construct a conductive surface that reflect antenna power in a desired direction, right? So we can also use reflectors in order to have the desired direction of the antenna power. May consist of one or more planes or may be parabolic, for example in case of a dish antenna, right? So typical reflectors are plane or corner reflectors. The parabolic reflector, that is the dish antenna. Okay, so here we have the expression for the antenna gain and the effective area. So this relationship actually define the relationship between the antenna gain and the effective area. So here you can say G is antenna gain, A is the effective area, carrier frequency, C is the velocity of light, and lambda is the wavelength. So G 4 pi AE over lambda square. So I can place lambda right is equal to C over F, right? So I will be having 4 pi F square AE over C square. So different antennas, they provide different effective area and gain. So for isotropic, this is the ideal case. So we have gain 1, which is not possible, right? And then we have half wave dipole, so the gain is 1.64, and then we have horn antenna, and the gain is 10A over lambda square, parabolic, right? And then we have again turnstile. So when we talk about the antenna communication, so there are different propagation modes, right? So for example, we have the ground wave propagation, and we have also the sky wave propagation, and there are different frequency ranges that are associated with those different propagation modes, right? So for example, in case of line of sight propagation, we have frequencies that are above the 3 megahertz. For sky wave propagation, we have frequency range of 3 megahertz to 30 megahertz, and for ground wave propagation, we have less than 3 megahertz, right? So here we have the scenario of the ground wave propagation mode. So here we have the transmission antenna, and this is the receiver antenna. So this is the way out how the signal will be going to propagate. So along the contour of the earth, right? So it will be the radiations or the radiated energy will be following the contour of the earth, can propagate considerable distance, so we can send and receive at a longer distance, and the frequency bands that are supported, they are ELF, right? VF, very high, very frequency, very low frequency, and then low frequency and medium frequency, extremely low frequency. And the range of the spectrum is 30 hertz to 3 megahertz, for example, AM radio. And then we have the sky wave propagation. As we know that we have a layer of ionosphere around us over the surface of the earth. So you can see that the transmission antenna will be transmitting the signal, and this signal will be reflected back and forth between the ionosphere layer and the surface of the earth, and then finally we have the receiving antenna, and the signal will be received from ionized layer of the upper atmosphere back and forth, right? travel a number of hops. So you can see that these are the hops back and forth between ionosphere and Earth's surface. So high frequency band with intermediate frequency range. So here we have the frequency range of 3 megahertz to 30 megahertz, and we can have the example of international broadcast. So here this is a very real example which we can look around us. For example, in case of cellular communication antennas, so there are two type of antennas. One are omnidirectional antennas, and the other one, they are the directional antennas. So here we have the line of sight propagation, so signal propagation. So one antenna is here and the other antenna is here, and they are aligned. So this is one of the requirement. So transmission antenna and the receiving antennas are in effective line of sight range, and both line of sight and the non-line of sight case. For satellite communication, signal above 30 megahertz not reflected by ionosphere. For ground communication antennas within effective line of sight due to refraction. So these are the frequency bands: very high frequency, ultra high frequency, and EF, extremely high frequency, infrared optical light, and the range is 30 megahertz to 900 terahertz. So on the higher side. So here we can make some of the line of sight calculations. So this is the D naught, right? And here we have the DR, right? So H and D. So H is the antenna height and D is the distance between antenna and the horizon in kilometers. So D naught is equal to line of sight. For line of sight, optical line of sight, D naught is equal to 3.57 H, and for effective or radio line of sight, DR is equal to 3.57 kH. K is the adjustment factor. So these are the line of sight equations: effective or radio line of sight, D distance between antenna and horizon, H antenna height, K adjustment factor. So maximum distance between two antennas for line of sight propagation is, it can be represented. So there are some of the impairments that we have to face when we talk about the line of sight wireless transmission: attenuation and attenuation distortion, then free space loss, noise, atmospheric absorption, multipath and refraction, then thermal noise, right? So multipath fading, refraction, thermal noise, so attenuation. So as the signal or the fields or the radiated electromagnetic energy moves on and on, so the signal becomes weaker and weaker, or you can say the strength of the signal falls off with the distance over the transmission medium. So as a result, we have attenuation. So there are certain factors that are involved when we talk about the attenuation. Received signal must have sufficient strength so that circuitry in the receiver can interpret the signal, right? Signal must maintain a level sufficiently higher than the noise, because when we have transmission at a longer distance, so there can be chances that the noise power or the noise level is higher than the actual signal. So in that case, it's very difficult to retrieve the actual signal, right? So attenuation is greater at higher frequencies, causing distortion. So here we have the expression for the free space loss. So this is the transmission power and this is the received power. That is equal to 4 pi d square over lambda square. Lambda carrier wavelength, propagation distance between antennas, the distance between two transmission and, or you can say distance between transmission and receiving antenna, c is speed of light, and lambda is the wavelength. So here we have converted free space loss into, or represented into dBs. Again, so there are some different types of noise which we come across when we talk about the noise, when we have to transmit signal from one point to another point. One is the thermal noise, and then the other one is the intermodulation noise, crosstalk, and impulse noise. So thermal noise occurs as a result of thermal agitation of electrons. So as when we talk about the communication, and in order to transmit and receive signals, so there can be repeaters in between, there can be devices, electronic circuitry that is involved in order to achieve the transmission and reception. So in that case, we have to come across the thermal noise that is actually produced due to the thermal agitation of electrons. So it can be a function of temperature. So thermal noise is uniformly distributed across the frequency spectrum. Hence, it is referred to as the white noise, or you can also term it as Gaussian noise. So it cannot be escaped, or so places an upper bound on the communication system. Right. So here you can see that we have transmission, the data that has to be transmitted, and this is the noise and signal plus noise. So now the noise and the signal are superimposed over here, and after sampling we received the bits, and you can see that here we have errors in certain bits. So here is the expression for the thermal noise. N naught is equal to KT, right? N naught noise power, and K Boltzmann constant, T temperature, right? So here we have to mention another type of noise, that is the intermodulation noise. Actually, if we talk about a signal, so there are a lot of different frequencies that are present within a single signal, right? So if the signals with different frequencies share the same medium, so what happens that different signals, they can be attenuated differently, right? So interference caused by a signal produced at a frequency that is the sum of, or the difference of, original frequencies, those fundamental frequencies actually. So then we can have our intermodulation noise. Then we can also have the coupling between different communication paths, and we also have the impulsive noise. So one of the important when we talk about the data communication is the signal to noise ratio. So ratio of the power in a signal to the power contained in the noise present at a particular point in the transmission. So we normally measured this signal to noise ratio at the receiver with the attempt to eliminate the unwanted signal, that is the noise. So it is represented in dBs. So we have PS over Pn, where PS is the signal power and Pn is the noise power. So higher SNR means better quality of the signal. So it is again in dBs, decibels. So here we have the expression for energy per bit to the noise power density, right? So EB over N naught. So we can then have S over R over N naught, right? Bit error rate for digital data is a function of EB over N naught. There can be some other reasons for impairments: atmospheric absorption, multipath fading, and refraction. So multipath propagation. So reflection occurs when signal encounters a surface that is large relative to the wavelength of the signal. Diffraction, scattering. So these are the multipath. They can be multipath propagation and multipath fading also. So multipath propagation, multiple copies of a signal may arrive at different phases. So we can receive the signal with different phases, right? So then we have intersymbol interference. Copies of the pulse may arrive at the same time as the primary pulse for a subsequent bit, right? So here we have the different type of fadings: fast fading, slow fading, and then flat fading, selective fading, relay fading, and Riccian fading, right? So then we have some error compensation mechanism, forward error correction, adaptive equalization, and diversity technique. So in forward error correction, transmitter adds some sort of error correcting codes to data block, right? So the code is a function of the data bits. So receiver, on the receiver side, the calculations are being made in order to correct the errors if there are some errors in some of the bits. If the calculated code matches incoming code, no error occurred. If the error correcting code does not match, receiver attempts to determine bits in error and correct it. So error correction and then error detection. And then adaptive equalization. So it can be applied to transmissions that carry analog or digital information. We can have voice and video communication, right? So it's actually is used to combat intersymbol interference, adaptive equalization. So what is the technique involved? It's gathering dispersed symbol energy back into its original time interval. So there are certain techniques that are involved when we have to apply the adaptive equalization, lumped analog circuits, and sophisticated digital signal processing algorithms in order to have the adaptive equalization. Then we can also have the diversity technique. This technique is based on the fact that individual channels, they experience independent fading event, right? So there can be certain reasons, space diversity, right? Techniques involving physical transmission path, and then we have frequency diversity techniques where the signal is spread out over a large frequency bandwidth or carried on multiple frequency carriers. So we can also have the time diversity. So three different types of diversity, right, techniques: space diversity, frequency diversity, and time diversity, aimed at spreading the data out over time. So here we have the application of the antennas in wireless computing, right? So we have a scenario, for example, within building we have already an infrastructure that is actually based on the LAN, local area network, and over that LAN we have different services, different apps, different applications are being running, and different services are being offered that includes voice, video, and data services, right? And we want to extend that LAN in order to provide in order to cover longer area, right? And the problem is that we cannot lay down physical cables due to some reasons or due to some problem. So what we need to do? So we can have the provision of wireless LAN. So the existing LAN will be acting as a backbone. So at the top we will be laying down the wireless LAN. So in that case we have to take into account few factors: the technology, so that the wireless technology will be compatible or will be communicating with the existing or using these existing LAN infrastructure as a backbone. So there should be a frequent data transmission and reception between the backbone, that is the LAN existing infrastructure, and the wireless. So technology. So in that case, for example, if I'm asked, I will be prefer the Wi-Fi technology in order to have the wireless LAN or establish the wireless LAN. Then, of course, we don't want to install huge antennas, right? So we will be also considering the antenna that are the important. So by using the transmission and receiving antennas. So another problem that I know that the devices which are owned by different employees, different people, they are having the Wi-Fi antenna. So of course I will go for the or opt for the Wi-Fi. So this is another factor. And then the cost. This is also very important. So I don't want to invest more. So and I don't want to you can say that in fact most of the existing infrastructure. So in that case, I want to take into account the cost. So in that case, I will go for the Wi-Fi, or I can lay down the Wi-Fi infrastructure. So all the services, they are accessible by using this technology, and this existing LAN infrastructure will be acting as a backbone, providing all the services to the, and in that way, with cheaper cost and with the integration or with the compatibility, all the issues have been taken into account, and I will be providing the services or extend the existing infrastructure, and now the services are being used, and we can also have the mobility support, right? So these are the one of the uses of the antenna in our scenario. So that's all for today's lecture. So we will continue to have review questions from एंटेना एंड द प्रोपगेशन इन आवर नेक्स्ट लेक्चर. सो आज के लिए इतना ही काफ़ी है. मेरी तरफ से अल्लाह हाफ़िज़, अपना ख्याल रखिएगा. अस्सलाम वालेकुम. Okay, let's have complementary session for lecture number 16, and we will be solving some of the questions that are relevant to antenna theory. So here we have our first question. So what we have to do, we have to find the optimum wavelength and frequency for half wave dipole antenna, and the length of the antenna is 10 meter, right? So what we need to do, we need to use the formula that is F is equal to C over lambda. See, length of a half wave dipole is 1/2 the wavelength of the signal that we already know when we talk about the antenna. So there is a correlation between the frequency and the antenna size. So 1/2 the wavelength of the signal that can be transmitted most efficiently. So as a result, the optimum wavelength that we should be having in this case is lambda is equal to 20 meter, and the optimum free space frequency over here is, we have to use F and C over lambda, where C is the velocity of the light and lambda is 20. So in this way we will get frequency is equal to 15 megahertz after some calculations. So here we have another question that within the depth in the oceans, right? So where the airborne electromagnetic signals can be detected grows with the wavelength, right? So this is a different scenario. So the military got the idea of using very long wavelength corresponding to about 30 hertz to communicate with submarines throughout the world. If you need to have an antenna that is about 1/2 wavelength long, so how long would that should be? So here we have a different scenario, and we have to perform underwater digital communication. So but we will be using the same concepts, same formulas. So as we know that we have the relationship between frequency and wavelength and velocity, that is C is equal to F lambda. So in this case, as we know that we have velocity of light that is equal to 3 into 10 raised to the power 8 meter per second, and 30 is given, that is the frequency, and here we will be able to find out the wavelength, that is 10,000 kilometers. Now we can imagine the size of the antenna if we have the wavelength of 10,000 kilometers. Half of that is 5,000 kilometers. So if we want to construct that antenna, so what we need to do, we have to build an antenna of enormous size. Even we can go from one Pacific to another Pacific, right? So that is not the possible use case. So we need to do something else, or we need to adopt some other mechanism in order to have underwater digital communication for submarines. So here we have another review question. The audio power of human voice is concentrated at about 300 hertz. So antennas of appropriate size for this frequency are impracticably large. So again, this is almost the same use case, that if we are going to build the antennas by taking into account the human voice frequency, so again this is impractical. So what we normally do, we use some carriers, right? Send voice, because we have to transmit voice from one point to another point by using different means. By radio, the voice signal must be used to modulate, so we have to use a carrier of high frequency, right? So the question over here is, what is the length of the antenna? 1/2 wavelength long for sending radio at 300 Hertz. If this is not practical, then alternate, what is the alternate? So is to use a modulation scheme as mentioned, right? So what should be the modulation scheme over there? And here we have the solution, right? So if we try to solve the first use case, that is taking into account 300 Hertz frequency, so again by using the same formula, right? So you can see that lambda comes out 1000 kilometer. So it means if we want to transmit the voice that is of 300 Hertz, so we need to construct an antenna of length 500 kilometer, right? So even we can travel from here to Lahore when we talk about this size of antenna. And an alternate is to use the modulation scheme as mentioned in lectures. So the bandwidth of the signal is a narrow band and centered on a carrier frequency, right? So over here you can say that the carrier frequency corresponding to lambda by 2 is 1m, is given by, right? So 150 megahertz. So we have to use a carrier in order to transmit voice, that is 300 Hertz, right? Okay, so here we have another question. Amount of people who receive radio signals in filling in their teeth. You have one filling that is 2.5 millimeter long that acts as a radio antenna, right? So that is, it is equal in length to 1/2 the wavelength. So what frequency you can receive? So here we have lambda, the wavelength is 2 into 2 raised 2.5, 10 raised power minus 3, right? So then we can again use the same formula, and the frequency comes out to be 60 gigahertz, that is on the higher side. So we will be receiving communication or data at this frequency. So here we have a very long question, right? So that if a source of electromagnetic energy, because we use electromagnetic energy in order to transmit data from one point to another point when we have to rely on free space, is placed at the focus of the paraboloid, that is relevant to the dish or maybe satellite communication, is a reflecting surface. So as we know that the paraboloid is a reflecting surface, so all the data, all the signals, they are reflecting towards the focus of this dish antenna. Wave will bounce back in parallel lines to the axis of the paraboloid. To demonstrate this, consider the parabola. This is the equation of the parabola. Y square is equal to 2px, and it is shown in figure over here. So you can see on your right hand side, and so here we have a point over here, this point P, right? And on the parabola, and PF is the line. So again you can see the line from focus to this P point, that is PF. Construct the line L through P parallel to x-axis and the line M tangent to the parabola at P. The angle between L and M is beta, and the angle between PF and M is alpha, and the angle alpha is the angle at which a ray from F strikes the parabola at P. because the angle of incidence equals the angle of reflection. This is again the concepts from light, right? And the ray reflected from P must be at an angle to M. We can show that alpha is equal to beta. The angle, that is the angle of incidence, is equal to angle of reflection. We have demonstrated that rays reflected from the parabola starting at F will be parallel to x-axis, right? First, so here is the statement of the question. Now the actual questions are going to start. We have to show tan of beta is equal to P by y1, and then we have to show tangent of alpha is equal to P by y1. So because we need to show that angle of incidence is equal to angle of reflection over here. Okay, so first we have to take the derivative of the given equation, that is y square is equal to 2px. And if we take the derivative with respect to x, so you can see that we got 2y dy over dx is equal to 2p, and we are left with dy by dx, that is the slope by is equal to p by y. So therefore tangent of beta is equal to p over y1, and the slope of pf is, so we know that in case of we have 2 points on a line and we want to find the slope of the line, so we have to use this formula, y2 minus y1 and x2 minus x1. So this is the slope of a line. So we are using the same formula, y2 minus y1 and x2 minus x1. So now we are going to calculate tan of alpha. So y1 over x1 minus, so this is the expression. So finally, as we know that we have, if we put those coordinates in the given equation, that is y square is equal to 2px, right? So we are going to replace y1 square is equal to 2px1. So here we will have the simplification, and tangent of alpha will become p1 over y1, and that is equal to the tan of beta. So it means we proved that the incident angle and the reflected angle, they are equal. So that's all for the complementary session.